you want to restart?
That is a good idea.
Okay,
Hey,
this time I will be
but
quiet.
actually, you know what? Since we just launched, we just give it a minute or two for people to join, and now you have a chance to check if you can share your screen.
Yeah, go
Do I
ahead.
choose screen or presentation?
Um, Good question. I usually just do the screen, like the screen share, and then you can choose either
Yeah,
window
I'm glad. I'm glad we did this. I'm gonna have to restart. I don't know how to preemptively do this.
oh, permissions.
Yeah, bear with me here.
No problem. Well, we're gonna take a
You
full
see in a
like
moment.
yeah, we'll take a few minutes here.
Oh no, I don't have to reset. All right, but I don't know how to get my notes. So luckily, I wrote it in the Apple Notes app. So I'm gonna just have
Nice.
my phone here, and I think that'll be a pretty good solution. Okay, I can stop sharing for a moment then while we introduce. Okay.
All right. Yeah, and that was basically about a minute or 2 minutes. Hey, welcome everybody. Thank you very much for being here. Today is another Resonate webinar. Today we talk about DST, deterministic simulation testing. Now, before we talk about deterministic simulation testing, I quickly want to talk about our biggest company event this week, and that was our launch on Monday. So about 2 years, no, actually exactly 2 years ago, exactly in June 2023. Man, David, time flies. In June 2023, David and I started Resonate, and we only had like one mission on our mind, and that is best embodied in the slogan complex problems simple code. So we really wanted dead simple programming model that's dead simple to understand, dead simple to develop with, and dead simple to operate. So now, after 2 years of intense working on that vision, we are super, super happy to have released the Resonate server and the Resonate Python SDK. And so with that, please go ahead, please try it. We are always available for your feedback, of course, on GitHub, but also in the Discord at resonatehq.io/Discord. Please join the Discord, say hi if you haven't done so yet. And I'm also going to share the link to the launch post that went out on Monday in case you haven't seen it yet and want to read about it. Okay, so after 2 years, what made us be confident to say, well, we're ready for prime time? A big part of that is our testing strategy. And it's like, I want to say that deterministic simulation testing was an actual game changer for us. It increased our confidence in the correctness of the server by, it's like, many times over. And we eventually, like, were so convinced that DST is the way to go that we also implemented DST in the Python SDK. So now we have deterministic simulation testing in the Python SDK and on the server. And with that, we had the confidence, after the DST basically gave us a thumbs up, we had the confidence that our solution is a solution that actually is like delivers on its promises of reliability and simply just its correctness, right? And so today we have another webinar about deterministic simulation testing. Now, when I talk about deterministic simulation testing, then I talk all big about concepts and formulas and formal modeling and whatnot. So then the rest of the team was like, Dominic, we can't have you talk, right? We need somebody who actually like implemented it, and let's talk about implementation concerns. I was like, all right, then all I'm gonna do is the intro. So with that, begrudgingly, all right, I'm gonna hand it off to Cully so he can give us an outline of what happens. And then even more begrudgingly, I'm going to give it over to David and Andres to talk about the implementation and not so much about the concepts.
Awesome. Thanks, Dominic. Yes, we're hoping to do some dives deep into how we've implemented DST. David led both those efforts, and we're really hoping to answer as many questions as we can today. The practical questions around implementing this as we can. So let me just pop this up. So today, yeah, Resonate plus DST. Really looking forward to going over this. I like this image here. Echo, our mascot, holding a diamond. Diamond is the toughest material out there, and that's basically what our components are like now. Super tough as diamonds, we like to say. Okay, so DST, we have it implemented now in both Resonate Server and the Resonate Python SDK. David Farr, he led both of those implementation efforts. So he's gonna lead us through this presentation. I will do my best to chime in and moderate if folks in the chat have questions. And what we're gonna try and do basically is just compare and contrast the implementations, because I think that's a really great way to get a very practical mental model of how these things actually come about. Again, questions are highly encouraged. Seriously, if you want us to dive deeper into any particular thing we're talking about, please, we will do our best to pause and go over those. We did get some questions in when people were RSVPing for this webinar, and we did our best to answer these in the presentation we're going to give. So, for example, as an entry-level distributed systems engineer, how could I get started? Another one about how do you start using DST? I think we will be able to touch on that a little bit through our presentation, and then hopefully towards the end, we'll be able to maybe David can give a recommendation on the best way to get started at its most simple level. But we will cover some of those points during the presentation. There's a couple Resonate specific questions here about durability implemented under the hood and Resonate's execution model. These are sort of off topic for the webinar, but I really want us to address these if we have time at the end. And then we've got some questions about determinism while implementing DST in Go and verification of the results. And both of these we will definitely cover in what we've got planned thus far. But again, if you got a question, please, we'd love to hear it. So without further ado, I'm going to pass this off to David. We're going to start. Oh, sorry. Actually, we're going to start. So we're going to start with a quick overview of the components. Then we'll compare, talking about steppable core, controlling determinism, and assertions being your friend, and contrasting the validation, language specifics, and component specifics. So yeah, without further ado, David, I'd love to hand it off to you. And
all right.
What is it? What are these components that we have? What do they do, and why is it important that we have such great testing with them?
All right. Hi, everybody. I'm David. I'm the CTO here at Resonate. First off, let me start by saying, before I started at Resonate, I had never even heard of DST, let alone used it before. And now, after 2 years of working and building Resonate, I wouldn't even start like any project of any consequence without DST and without thinking about it from the very beginning. So it's very quickly become very integral to what we do here at Resonate. I would go so far as to say that we were unable to implement the SDK without it. We had initially had an implementation without it, but we had to strip back to the very beginning and rebuild it up with DST, and the differences really do speak for themselves. So I want this presentation to be like very practical. There aren't really slides here. I'm going to show my screen. I'm going to show some real DST runs on both the server and the SDK. We can look at the way that we do validations and verifications. They differ quite substantially between the server and the SDK. You will likely notice that the level of rigor and just the level of maturity is much greater on the server than on the SDK. This is no surprise. We've been doing a DST on the server for 2 years now, whereas DST on the SDK is very nascent. It's very new. So it's going to take some time to kind of work that muscle and kind of get that up to the maturity level that we have already on the server. And I do want to preface this with one caveat. This is two examples of how we implemented DST here at Resonate. It's certainly not the only way to do DST. There are numerous ways. These are only two implementations that work well for us. They've gone through many different changes, and they will continue to evolve and change. So this is not a prescription for how to do DST. It's just one possible way or two possible ways that you might do it. All right, so I've already mentioned today we're looking at two projects. We're looking at the Resonate server. The Resonate server was the first project that Dominic and I started when we started Resonate a few years ago. It is written in Go, and DST is therefore also implemented in Go. And we're also looking at our Python SDK, which is, of course, Python. So we've got like two implementations of Resonate on, I want to say, like two very different languages, which kind of shows the versatility of this this approach. So if you want to check out these code bases today, they're on GitHub. If you haven't done so already, check out our GitHub organization. And okay, before we dive into anything, I do want to quickly tackle like the very first question that we always get about DST. And it's specifically for our server implementation. We always get asked, how do you implement DST in Go when Go routine scheduling in Go is by design non-deterministic? And I have what's probably going to be a very unsatisfying answer for anybody, but I will explain. And the answer that I like to give is, well, use Go routines strategically. Okay, that's not very satisfying. So consider this. Hash map iteration in almost every language out there is non-deterministic as well. So how would you do DST if you needed to iterate over a hash map in the language of your choice? Well, you could either one, avoid it, or two, maybe you pre-sort the list before iterating over it, right? So the key here is we need to be aware of where non-determinism exists in the languages that we're using, and we need to mitigate it. That is, we need to make the non-determinism observably determinate. And that's exactly what you do when you pre-sort a list. And that's exactly what we do in our implementation of the ghosts of our Resonate server. This is not an easy undertaking. The way that we have tackled this problem is we've implemented a coroutine library called GoCoro, which you can also check out on GitHub. And we very strategically manage Go routines. Effectively, all Go routines in our system are simple handoffs, where like one Go routine hands off to another Go routine. That Go routine does something and hands something back to the scheduling Go routine. Effectively, we've implemented our own scheduler. This has major ramifications for the entire code base. But for us, we were willing to implement that as a first-class citizen in our code base in order to write DST, to do DST. So yeah, we were able to like stomach and take on that overhead, but we think that the benefits that we got out of actually doing DST were well worth that investment. So this one in particular, it's not easy, but that doesn't mean that you can't make your Go programs observably deterministic, and that's exactly what we did, and we still use Go routines. All right. So let me share my screen. Cully, any questions so far?
Not yet.
Not yet. All right. Bear with me here. There we go. All right. Can folks see my screen? Thumbs up, maybe. Awesome. All right. Okay. So I promise we're going to look at code. I've actually put together a subset, like a sample of our code. I promise that this code is built on the real DST code that we have on our server. I didn't concoct this out of thin air. You can probably see a strong correlation between this and our actual implementation. And later I will dive into the actual implementation and answer any questions that anybody has. All right. So on a very, very high level, DST is composed of the following steps. One, we randomly generate a seed and hand the seed into the DST test. This is the only part of DST that is truly random. Random in quotes, so far as you would argue that any computer program can do actual random number generation. But for our intents and purposes, we can say that this step is in fact random, but we actually do it outside of the DST. So when we do DST in continuous integration, we actually generate that as part of our GitHub workflow, and then we hand it in as an environment variable to the actual DST run. So it's truly generated outside of DST. Once we have this seed, we seed a random number generator or a pseudo-random number generator based on the seed. From this point on, all randomness that we need in order to do DST is determined from this random number generator, and in doing so, we get reproducible runs. So given the same seed, the same sequence of random numbers will be generated on any subsequent run. So I'm showing this here by passing in a seed to DST. In Go, this is how you seed a random number generator, and we hold on to a reference to that random number generator, and from this we generate all the randomness that we need to in our DST run. With that in place, the first step of any DST run is to generate a set of requests. Now, our server has a natural advantage here over our SDK. The server has a finite number of requests that we expose through our API surface. Most of these requests correspond to promises. Promises need to be created, resolved, rejected, canceled, etc. But some of the requests correlate to other objects, specifically tasks, schedules, and logs. But what's nice about this is there is a finite on the server, a finite number of requests that can be generated because our API space is not infinite. It's well defined. In fact, there is an open API specification for it available online. Let me just quickly show that. And the requests that we generate correspond one-to-one to these requests. Of course, we're not making an actual network request. We're not opening a TCP connection. We're not making an HTTP request. We're going one level below that, but they are analogous. So every API request you can find in our open API spec. When I say we randomly generate requests, you can imagine that this is what we're randomly generating. So we're randomly generating an ID, and we're shoving that ID into a GET promise request. Or we're randomly generating a ID and a timeout, and we're shoving that ID and timeout into a create promise request or a resolve promise request, so on and so forth for every API that we expose. And in the sample code, you can see that for every step of the DST, that's what we're doing here. Now, let me step back for a sec. I forgot to mention the way that DST manages time is to choose some number of iterations, or we tend to call them steps, from the outset, and then run the DST from time 0 to some time corresponding to the final step. Now, the amount of time that passes on every single step can be defined by you. So you could say that a step is 1 second. You might say that a step is 10 seconds. On some level, it's arbitrary, and it's hard to say what is a good amount of time to assign to every single step. If you have a system running in production, you might have a handle on how many requests per second your application receives in production, and maybe you would want to generate those number of requests every, say, second, and then therefore for your system it would make sense to say that a step is just one second, and every single time we generate the average number of requests, plus or minus some variation that you can randomly throw in there, every second. For us, we don't have a SaaS offering yet, so we don't have insights into how many requests per second Resonate may or may not get. So we chose some random number. I think we generate between 1 and 25 requests every step by default, but we've made this configurable. And the exact correlation between a step and time is, I believe it is like 1 step is 1 second, but I don't even remember if that's the case, and it's completely arbitrary. Now, one thing that I totally forgot to include in the sample is that time is something that needs to be very carefully managed when doing a DST run. And the way that we do this is we hand time in from the outside. When we're doing a DST run and we're taking a step in a DST run, we can always map or translate the step number to time. And that's exactly what we do. So if we say that 1 step is 1 second and we want to measure time in milliseconds, then we always hand time in to the step function from the outside. And we might do so by doing something like this.
Hey, David, can I chime in real quick?
Go for it, Cully.
So just to add some context here, in terms of what is true for all the DST implementations thus far, is that your core of your system, right, has to be steppable. That's what makes this possible, right? So when you say step, basically the core of your system is, correct me if I'm wrong, but it tends to be single threaded, so that one thing happens on, like, it takes a step and it only does one thing at a time. And that's how you're able to move the system forward, right? And
that is correct. What is not shown in this overview here, but I will jump into the code in a sec, is the system itself. So right now we're only looking at how we see the system, how we generate requests, and how we put them into the system and get them out. But when the system takes one step itself, we're running it in effectively a single threaded mode. So in Go, that means one Go routine. We take some liberties with that, and that is by strategically managing the Go routines, as mentioned. If you dive into the internals of Go Coro, you will notice that there are Go routines or calls to functions made with the Go symbol. That is very carefully managed, and only one Go routine is active at a time. So we can reason that it is only a single Go routine, even though that is not literally the case.
Yeah, I think that's a real critical point we want to make, right? Is that the architecture of your system has to support DST, right? So DST really affects how you build your component. The core of it must be steppable. And so in your mind, like what are the simplest ways to do that? My understanding is right, you use either Go routines or I think in the SDK, right, it's generators or coroutines, right?
That's right. That's right. Go Coro is a coroutine library. We have implemented coroutines with channels and Go routines because that's what Go can do for you. And there is no native coroutine built into to Go. Not like there is in Python with like the yield, for example. So we had to build that ourselves. This is not a trivial undertaking. That took some serious developer effort, but the payoff of that was we got to do DST.
In the server, doesn't it? So what's the difference between a tick and a step when it comes to the server?
They're synonymous. That's kind of funny. We use them synonymously. So in the server, the function is called tick. I guess that's how we were feeling when we implemented the server. And on the SDK, the function is called step. I don't know why it ended up with a discrepancy, but you can imagine they're synonymous.
And I just happen to notice, right, in the server then, so when the server runs normally, it basically ticks forward on every, I think, what, millisecond? It just ticks forward?
Well, it ticks forward in physical time at the time that you get to the next tick.
Okay.
Now, that relationship to logical time is can be defined by you. So
Right.
at a minimum, you have to plus one. In fact, there's an assertion error somewhere deep in our code where if ever the clock tries to go backwards, we throw an assertion error, and I believe the message says the arrow of time only flows forward. That's true for the physical world that we live in. It turns out it's also true for DST. Now, the amount of time that you move forward can be up to you, and it doesn't even have to be fixed, right? So like at a minimum, you got to do one step forward. So like one whatever. If we just forget about the units for a sec, you can just say we're going forward by 1. Or you might say we're going forward by 100, or we're going forward by 1000. That is up to you. And it doesn't even have to be fixed. Now, we're not doing this, but if you wanted to be more optimal about it, you could introspect the state of your system and say, okay, there is nothing that needs to be done now for 1 hour, maybe, right? Where you say there's a sleep, like somewhere in my code, we did time.sleep 1 hour. There are no more incoming requests. Therefore, there is nothing that we have to do for a single hour. And at that point in time, you could convert the hour into ticks, and you could effectively say, we're not going to do another tick until this logical time, and then do another tick. Now it's very sophisticated. We're not doing that yet, but being able to fast forward time like that is very powerful, because it would really let you simulate even longer running DST runs. And I don't mean longer running like in physical time. I mean in logical time.
Would you be able to, because we're actually chewing through time here pretty quick, would you be able to jump to giving us a quick demo of the server DST run?
Yeah, did I talk too long?
It just time flies when you're having fun, I think.
Okay, I just wanted like very, very quickly. I have a few practical things to show. So
Awesome.
when you manage your Go routine strategically, you do end up in a situation where you might get into deadlock. Which, Cully, this relates to exactly what you're saying. Like you want to run DST with a single Go routine, but how do you do that in Go, right? Well, the way that because in the real world, which is my affectionate term for when we run the Resonate server in production, or really in any non-DST environment that's running in the real world. In the real world, you want to use Go routines because you want the benefits of concurrency and parallelism. So what do you do when you get to DST? Your interfaces are still communicating over channels, because it's still a Go program. But if you were to push or send to a channel, and there is no consumer consuming from that channel, you have deadlock. So this very practically, like how do we work around that issue? Buffer channels. Buffer channels are awesome. So we actually instantiate all of our we call them queues. So this is SQ, a submission queue channel, with some fixed number of maximum items. That way, the sender can send to the channel, and no one has to be receiving on the other side. And you can do that with a select case where you actually write the send in the case statement, and then a default. The default gets invoked in the case that the buffer channel is full. And not only is this how we get around the deadlock problem, this is also how we implement back pressure, which I think was one of the questions that we already got. Um, if the channel is full, we go all the way up and we reject the HTTP request. And we say exactly that. We say the system is full or busy or something like that. I do believe there is an HTTP error code that corresponds exactly to the situation. And then on the other side, where we're consuming, we don't want to consume or wait to consume for forever. So we consume in a tight loop when we get to that point. The for loop on the outside is some maximum number of messages that we consume every single step. But then on the inside, we actually implement our select case with the default. If ever the default is invoked, which indicates there are no more messages on the channel right now, we just return. We get out of there. So that's how we implement, how we avoid the potential deadlock pitfall. It's very easy to fall into when doing DST in Go. Okay, but without much further ado, let me show a DST run because that's where things start to get really cool. So I want to say, let me make this a little bit bigger. Bear with me here. So hopefully it's a bit more readable. We built DST into our binary, into our CLI. So this is not like a special part of the server that's only accessible if you clone the repo. If you have installed Resonate locally, you can also do a DST run. And the command for that is Resonate DST run. You don't need to provide any arguments at all. I'm going to provide a seed. I'm just going to say 7. And I am going to also limit this one to make the output a little bit more grokkable. So we're going to do 3 ticks, and we are going to do exactly 1 rec per tick. Recs per tick 1. So this is a very, very small DST run. This would not be practical, but for demonstration purposes, it's kind of cool. So we end up with this extremely small DST run, and we log all 3 of the requests that we are making. And after 3 ticks, actually more than 3 ticks, because we actually run until all the coroutines are complete. So that takes a few extra ticks, but 3 plus some amount of ticks, the DST run finishes. And whenever we get a response back from the system, right? So we generate 1 request, we enqueue it into the system. The system takes one step and control is returned to the generator. The generator moves on. It attempts to dequeue responses. There are no responses yet. So it moves back to the beginning of the control loop, generates a request. So the second request is create schedule. Enqueues that into the system, and then attempts to dequeue a response from the C queue, we call it, the completion queue. And at that point in time, we now have a request response pair. The request was the one that we randomly generated, and the response was the one that was provided by the system. And I want to clarify, like, this is our system, like this is the one that runs in production. It's the same response you would get if you made an HTTP request with the system in the exact same state. And you can actually see that here, we're not logging these request response pairs until we get a response. So what we're seeing here is the very first response to come back. I can see that this request was made at time 0. That is the timestamp before the vertical bar, and the result came back at time 999. It turns out for our linearization checker, which I will get to in a sec, it's better to have non-overlapping timestamps for requests and response, which means at tick 2, which maps to logical time 1000, all responses are assumed to have come back at time 999, and all requests are assumed to have gone out at time 1000. And they don't overlap in the system, and actually marking them as non-overlapping helps with linearization check later. So that's why you see 999 when logical time would actually be time 1000. So at time 1000 or 999, depending on how you look at it, we do get a create callback response. And here, just like briefly glancing at this, I can see that the request that we randomly submitted failed with a 404. Why did it fail with a 404? Well, the corresponding promise, so callbacks are registered against promises. And this is, we start with an initial state. There is no information in the system at all, therefore no promises. And this callback was attempted to be created against the promise, which does not exist because we're in this initial state. So a 404 is to be expected here. Same with the read schedule. So the second request that we generated attempted to read a schedule which does not exist, and we get back a 404.
David, this would be a great time to maybe just touch on how assertions are your friend here, because you're pointing out, right, the 404 is expected. Basically, that's not an error, right? The system, you're firing off a request or something that doesn't exist. The valid or whatever's checking this will know it doesn't exist. So it's not an error. You should get a 404 in this situation. But you have assertions embedded throughout the Resonate server code such that if something happens, right, that you're not expecting, you would catch it then. You would actually see an error pop in this DST run.
Yeah, totally. So yeah, assertions are friends. I have to admit, when I started this process 2 years ago, I was a little bit less sold on this assertion-based development style. So those assertions are littered in the code base. They're not in the DST, in the testing, in our test files. They are in the actual code base. And effectively, wherever there might be a path in your code base where you do not expect the control to ever get to, or some result that is like technically possible as per the type system, but maybe you never expect to see, just write an assertion for that. And if you look, especially at our Python, because by the time we got around to the SDK, I had embraced the assertions a little bit more, so they're a little bit more widely used in the SDK. But nevertheless, if you jump into the Go code, you will very quickly see assertions. Go does not have assert; it doesn't exist. So we wrote a util.assert, and if you were to look at the implementation of util.assert, we panic. So when we say assertions, in Go, we effectively mean panic.
So it's kind of like you're actually like this system, right? Would not, if it hit an error in production, it would panic completely. But
Yeah.
but you rarely, because of DST, you would never see it because the DST runs are constantly going, checking, and would hit these assertion errors, and thus you would be able to fix these bugs well before you even hit production.
Yeah, that's right. I wouldn't put it past once your system is used in production, it seems to find like incredible outcomes. But that is true. Like we have such high confidence that DST has found like 99.9% of the possible code paths that we don't expect to see assertions pop up in production.
And let me chime in here real quick on the assertions because you're touching upon a very important topic. And there I do get to talk about concepts just a little bit. And that is systems are generally categorized or they're defined by two properties, safety and liveness. Safety means nothing bad will ever happen. And liveness means something good will eventually happen. If your system like travels down the happy path, right, you generally get safety and liveness. But there comes a situation where you may have to prioritize. And just like, what do you prioritize? Do you prioritize safety or do you prioritize liveness? Now, there is no general answer to that. That is very much up to you. But in our design philosophy, we figured that if we violate an assertion, right, a core assumption about our system, even during a production run, if we violate a core assumption, something is really going bad, right? Therefore, shut it down. Just stop, right? Because that means you are not transitioning from a consistent state to an inconsistent state. So you're prioritizing safety very, very harshly, safety over liveness. I also want to take the opportunity and mention that a lot of what you have heard today may have reminded you of a different project, and that is Tiger Beetle. And that is no accident. We took a lot of inspiration from Tiger Beetle, not just in general in systems engineering and systems design, but also very specifically in terms of DST. But so when we talk about, for example, when we talk about DST, when we talk about assertions, when we talk about assertions in production, you will find a lot of that in Tiger Beetle's design guide and style guide that is called Tiger Style and is available on the tigerstyle.dev. So if you wanna look into another project that uses DST very successfully and also is a shining star and guiding beacon when it comes to systems thinking, systems design, and systems engineering, I highly recommend have another look at Tiger Beetle and also Tiger Style to get some inspiration for your own project. All right, thank you very much. And then I hand it right back to David. Thank you very much for the microphone.
Awesome. Okay. I realize that we're starting to get pressed for time, so I'm just going to very quickly show what we do to verify these runs. So I think we can see you can run a DST locally. I'll let me run like a larger one. So I'll just run with the default settings really quick here. Just resonate DST run. you can see there's a lot more information flashing on the screen, and we end up with this collection of request-response pairs, quite a large collection of request-response pairs. You can imagine we could keep this running for quite a bit longer too. Then the question becomes like, what do we do with this? Like we have all this information, we have generated all this information, we have not come across an assertion, so we can reason that our system at least did not end up in an inconsistent state, one that we absolutely do not expect to see. However, we cannot fully reason that our system is correct at the moment, because we don't know. We just never hit one of those assertions. But even knowing that we never hit one of those assertions already gives us quite a bit of confidence in our system. In fact, in the current implementation of DST on our SDK, we are relying solely on not hitting assertion errors, because we haven't built out any additional validations yet. We plan on doing so, we just have not gotten there yet. And even that alone has given us like great confidence in our SDK. But the server is a bit more mature. It's been around a little bit longer. So we've actually gone one step farther, and I'll just quickly jump into the actual code. So like, if you look at DST, we have a validator, and in this validation, we actually look at every response, and we verify that the response is internally consistent. That is, it's consistent in and of itself. It's what there isn't any like oh, if there's a promise that you say is resolved, it's not pending. Okay, that's good. But not only is it internally consistent, but also that it is valid in accordance to some model that we build up. And this is quite a bit of work, and it effectively implements a very simplified, but nevertheless a new version of the system altogether. So for every response we get, we add it to the model. If it's internally consistent, we add it to the model. So what that means in practice is, if we get a create promise response and it is successful, it's a 201, so we know that the promise was in fact created, then we add that to the model. If ever we see a response, a create promise response with the 201 for the same promise, then we know we have an error, because a promise can only be created once. It can't be deleted. That's a very simple example. The model is checking much more than just that, but you can see how over time, as these responses come back, our model builds up bigger and bigger, and there's more to check against on any subsequent response that comes back. Okay, so that in and of itself is already pretty good. That's a pretty good validation. But we actually go one step farther. I would say this is about as far as you can go with DST before you need to kind of like stop your DST journey and move into the world of formal verification. We go as far as to do a linearizability check. Please don't ask me exactly how the linearizability checker works. I have read the papers, but my understanding is very practical. And we decided to not implement those papers ourselves. In fact, we're using a third-party library called Porcupine, which is a fantastic library. I definitely do recommend it. But the model that we wrote corresponds to Porcupine's interface. And therefore, we can actually seed our model into the Porcupine checker. And at the end of every DST run, this is exactly what we do with those request response pairs. Check operations verbose. We seed all the ops. These are the operations, which is just a list or a slice of those request response pairs into Porcupine. And Porcupine verifies the linearizability for us. So on a very high level, just really quickly, and this is probably wrong, what the linearizer is checking for is that there exists some path through the system that maintains a consistent state where the state is consistent as defined by our model. Why is that hard to check? Well, the whole point of DST is, well, one of the reasons that we do DST is to simulate partial order. So with concurrent systems, every single time we fire off a set of requests, we don't know at what time and in what order those requests are actually acted on by the server. So if we fire off 10 requests, actually, let's make that number much smaller. Let's say 3, A, B, and C. We don't know if the server is actually going to operate on those requests in order ABC, or maybe order ACB, or maybe order BAC, so on and so forth. And that order could be all possible permutations of all requests that are currently in the system. And that state space blows up very fast. And in fact, the time complexity of linearizability checkers, even a well-implemented one, is substantial. I don't know what it is off the top of my head, but it's very easy to seed Porcupine with enough operations to never get a response. So we have to be very strategic in how we seed Porcupine with our list of operations, and we do partitioning on that, and it was a fair bit of work to get it working. But once it's working, what we get is, I believe, the strongest consistency guarantees that we can get, short of formal modeling. And in fact, when you do formal modeling, you're not doing it against your code. This linearizability check is acting against the actual code base. So you could make an argument that it's even better than formal modeling. Sorry, Dominic. All right, and Porcupine is pretty awesome because Porcupine generates a visualization of the DST run. So I'm actually going to go ahead and open this up. It opens up in the web browser, and I'm going to go ahead and open this one up. And this is very verbose, so it is tough to read. There are in fact lines going everywhere, but just know that every box represents one of these request response pairs. The left side is when the request was created, and the right side is when the response was received. And what we are seeing, what the lines represent, is a valid path as defined by our model through the system. And the reason why you are seeing quite a few lines versus just a single line through the entire system, in fact, initially when we implemented this, there was only a single line through the whole system. But the reason you see multiple is because we're heavily using partitioning. We can reason that one promise cannot affect another promise. So therefore, we partition based on the promise ID. And this increases the efficiency of the linearizability check substantially, which is why we're doing this. So if I mouse over, say, P1, we're looking at the linearizable path for all requests fired against promise P1. The initial read promise request came back with 404, but the second request was a create promise, which I can see succeeded. And then if I scroll this way, you can see that there is quite a ton of information. Eventually, I will find a complete promise. And the very first complete promise, which is happening here with request ID 79, is the one that successfully mutated the promise. Now, the promise can only be completed once. So if I keep scrolling, any subsequent complete promise request is going to fail. And that's probably what we're seeing down here. Yeah. And I just want to just quickly kind of like scroll here. You can see that this ends up being quite huge, right? And this is a DST run that ran in, I don't know, like 3 seconds maybe. We can run this stuff for hours. Linearizability check becomes kind of hard, maybe even impossible if you do a DST run for a few hours. But you can at least verify that the assertions never got hit. Uh, and you can only imagine the different scenarios or situations that this is capable of finding that traditional testing or unit testing would just be completely incapable of finding. So this has really been, I think, our secret weapon for creating Resonate. All right, I'm looking up and I'm noticing that we have 5 minutes left. So Cully, I want to uh, hand it back to you to see if there's any questions. I'm thinking maybe we don't get to Python today.
Yeah. So somehow we managed to get by without any direct questions in the chat. However, um, there were definitely a couple questions from folks who RSVP'd about just getting started. And if so, last few minutes here, what would be your very practical advice for anybody looking to get started in DST?
Can I take that?
Please
Yeah,
do.
yeah.
And I promise no concepts, except just a few concepts. So um, you have to think about this, like what the structure of your system is, right? And especially if we talk about a distributed system, how do we generally think of a distributed system? Generally, we think of a distributed system as a collection of components, right? And these components communicate by exchanging messages. So the very foundation of communication in this mental model is message passing. And we also mentioned the stepability, right? So other or the same mental model generally also reasons about a distributed system as any one component taking one step at a time, right? There's a fantastic blog post by Martin Kleppmann. It's called Verifying Distributed Systems with Isabel. And he very carefully and clearly lays out that mental model. Now, when you want to build your system according to that mental model, you will actually be confronted with some of the abstractions of software systems that contradict that somewhat. And so, my practical advice is do not rely on TCP connections. Right? That is the very first step. Of course, right? There's, like as David mentioned, you have to be able to control non-determinism, right? There, no doubt about it. Right? That is the very basis of it. So you have to be able to control what David called your scheduler, or what often is also called your event loop, right? You have to be able to control event loop, because that is what drives your system forward. But one of the worst offenders that makes this really, really hard is TCP connections. Why? Because a TCP connection, you have this software, right? If a component takes a step, imagine you have a step function, right? You call it, it returns. And then the scheduler calls another step function with a different component. It calls it, it returns. Different component. It calls it, it returns. TCP connections do not work that way. All right. If you call it somewhere down the stack, you block on it, right? So now you have a function that does not return. Right? And you basically also, as David mentioned before, you have a deadlock at that moment, right? Because the component that would actually work on this request giving you an answer cannot be called, because that would be another call to the step function after your step function returns, which it doesn't. Right? So TCP connections are pretty detrimental. Now, I know that there are other implementations of DST out there that try to actually work with the abstractions that the operating system give them. But one of the most practical, biggest pieces of advice: find the right environment abstractions. more of an opinion probably, but first off, find the right environment abstractions. And now my opinion, TCP connections are not it. If you can develop your system around message passing semantics, because then you basically shoot a message, right? And you're done with, and your step function returns. And that is what we implemented in the Python SDK, because the Python SDK needs to simulate an entire distributed system within one Python process, including the network. And we really hit our head against the wall for a very long time. There were problems we couldn't push past until we identified it's in the TCP connection. Soon as you drop the TCP connection as a core abstraction and go on to message passing, you have a winner. Now, of course, in the real implementation, or in the real world, David called the real world, when you run it, right, your environment abstraction, that communications bus, is going to use TCP connections. That's not at all a problem, because you're not exposing that TCP connection to the user code. Fantastic, right? Because then in the DST world, you have a different implementation of that communication bus. All it does, it gets a message, and then eventually it will hand you a message. So, and now you broke this blocking behavior of a TCP connection, where it is the operating system kernel that basically wrests control from you, right? And that is what you want to avoid. You have to control your event loop all the time. Very practical advice. However you do it, find the right environment abstraction. Opinion, but informed opinion, TCP connections are probably not it. Invest in message passing semantics, and you are 80% there to implement your own DST.
Awesome. So we are totally at time here. We chewed through that hour real fast, and it turns out there's a lot more to talk about. So, good chance we will revisit this topic and put out some more articles on this, on DST and how we've approached it from our components. We have plans to add more components to our product base, and rest assured we will absolutely be implementing DST in those as well, and continue to refine our techniques and hopefully provide some more insights in what we're learning here, because I think one of the biggest takeaways I have from watching this team implement DST is just the insane level of confidence that David, Dominic, and Andres, and our other team member Tomas gains from having components that have DST implemented. They just feel very, very, very confident about the quality at that point, and that's really cool. That's something that I've taken away. It's rubbed off of me. It's something I've been thinking about, and there's definitely a pattern here, and I think we'll definitely try to explore that pattern and provide some insights on the pattern that's happening here more and more. So, yeah, thanks for joining us. If you have any questions at all, we'd love to hear them. Drop into our Discord, resonatehq.io/Discord. That's the place to be.
DST
now. Yeah, DST, distributed systems, Resonate. It's all good. Even AI turns out, it's great for AI as well. So if any of those things resonate with you, pun intended, drop in the Discord. Would love to chat with you. And yeah, thanks for showing up. Thanks for watching, and we'll see you in the next one.
Thank you very much, everybody.
Bye, everyone.
Thanks, David. Thanks, Collie. Thank you, Andres.
Thanks, David.
Thank you, everybody who joined. Bye-bye.
All right, peace out.